Hey everyone, and welcome back for another deep dive. Ever feel like you're playing catch up with all the machine learning hype?
hmm
You've got your Python, you've dabbled in TensorFlow, but still something feels
Yeah.
missing.
Yeah.
Like maybe you're just scratching the surface.
Right.
You, my friend, are not alone.
It's like having a top-of-the-line espresso machine, all the bells and whistles,
Right.
but you're still using instant coffee.
Bruh.
You might get a decent caffeine fix, but you're not really experiencing the craft.
Yeah, but I love that analogy, and you're spot on. We're tackling this head on today, diving deep into the math behind the machine learning magic. We're using an insightful Medium article by Mohammed El Rafay as our guide, Machine Learning Tools or Concepts. And you know what? The title alone sparks some serious debate in my head.
Yeah. He makes a compelling point in the article. Tools like Python and TensorFlow, as amazing as they are just that, tools.
Right.
They help us implement ideas, but the true power of machine learning comes from understanding the underlying math.
So it's like knowing how to bake bread from scratch versus just popping a pre-made loaf in the oven.
Precisely. Knowing the why behind the what lets you troubleshoot when things go wrong, adapt to new situations, and even come up with your own innovative solutions.
All right, so let's get this bread baking, shall we? This deep dive is all about unlocking that deeper level of understanding, even if you're not a math whiz. We're going to break down the key mathematical concepts fueling machine learning, and trust me, it's way more exciting than your high school algebra class. No pop quizzes, I promise. All right, so let's unpack the essential math ingredients in El Rafay's machine learning recipe. He breaks it down into three main areas: linear algebra, probability, and calculus. You know, just your average everyday conversation starters.
Right. Don't worry. We'll,
Uh,
uh, we'll make it digestible. Let's start with linear algebra. Think of it as the backbone of how we represent data in a way that machine learning algorithms can understand.
okay, because normally when I think algebra, my brain goes straight to solving for x. Not exactly thrilling stuff.
Right. We're going to talk about data here, not just abstract equations. Imagine you're plotting data points on a graph. Each point can be represented by a vector, which has both a magnitude and a direction.
Like an arrow pointing to a location on a map.
Exactly. Now imagine a whole bunch of these arrows, all organized in a specific way that's a matrix.
Okay.
And it's a fundamental way we structure data in machine learning.
So if I'm picturing a spreadsheet with rows and columns of data,
Yes,
that could be a matrix.
let's got it. And what's cool is that linear algebra gives us tools to manipulate these matrices, add them, multiply them, even rotate them. It's like having a set of power tools for data transformation.
Okay, that's starting to sound a bit more exciting than high school algebra, but how does this actually play out in like a real-world machine learning problem?
Let's say you're building a facial recognition system.
Oh, okay. Each face is essentially a bunch of data points representing things like the distance between your eyes, the width of your nose, and so on. Linear algebra helps us represent these features as vectors and then compare them to other faces in a database using techniques like vector norms.
Vector norms. That rings a bell from the article, but I'll admit I skimmed over that part.
Yeah, so essentially, vector norms help us measure distances between vectors, or in this case, between different faces in our data. There are different ways to measure this distance L1 norm, L2 norm, each with its own strengths.
So it's like saying, okay, these two faces are pretty close together in terms of their features, so they're probably a match. But using math to be precise about it. Precisely. And choosing the right norm can actually impact the accuracy of your facial recognition system. It's all about understanding the nuances of your data and the problem you're trying to solve.
Wow, okay, I'm starting to see the light here. We've gone from plotting points on a graph to facial recognition in a matter of minutes. This is way cooler than I thought.
And we're just getting started. Let's move on to our next ingredient, probability.
All right, probability. I'm a little more comfortable with this one. It's all about chance, right? Like flipping a coin and getting heads or tails.
Now, that's the basic idea, but probability in machine learning is a bit more nuanced. It's about understanding the likelihood of different outcomes given the data we have. Think of it like this. You wouldn't bet all your money on a horse race without looking at the horse's track records, their odds, and maybe even the weather conditions right.
Definitely not. I like to think I'm a strategic gambler. Well, at least when it comes to board games.
Exactly, and that's what probability helps us do in machine learning. Make more informed predictions based on data. Let's go back to our spam filter example.
Oh, yeah, the classic spam filter. I feel like that's always the go-to example for machine learning.
It's a good one because it illustrates the power of probability. Every time your spam filter encounters a new email, it analyzes the words, the sender, and other factors. Probability helps it determine how likely it is that an email with those characteristics is actually spam.
So it's not just randomly marking emails as spam, it's making a calculated guess based on patterns it's learned from previous data.
You got it. And one of the key concepts here is Bayes' rule, which sounds fancy, but it's super useful.
Okay.
It's basically a way to update our beliefs as we get more information.
So like starting with a guess and then refining it as we get more data.
Exactly. Let's say your spam filter initially thinks any email with the word free is spam. But then it encounters a bunch of legitimate emails from your friends also using the word free. Bayes' rule helps the filter adjust its understanding and become more accurate over time.
Okay, that makes a lot of sense. So we've gone from plotting data points with linear algebra to understanding the likelihood of events with probability. What's next?
Time for the grand finale, calculus.
Oh boy, here we go. Calculus was always my mathematical nemesis. Too many squiggly lines and Greek letters for my liking.
I hear you, but trust me, calculus is the secret sauce that makes a lot of machine learning work. It's all about understanding change and optimization.
Change and optimization. Okay, I'm intrigued. Tell me more.
Remember how we talked about finding the best values for our model's parameters? Like adjusting the recipe to make the perfect cake?
Yes, I'm all about that cake analogy.
Well, calculus, and specifically a concept called gradient descent, is what helps us do that. Helps us navigate a complex mathematical landscape to find those optimal settings.
Okay, that sounds pretty abstract. Can you give me like a real world example?
Imagine you're trying to teach a machine learning model to predict house prices based on features like square footage, location, number of bedrooms. Calculus helps us figure out how much each of those features influences the final price and how to adjust our model to make more accurate predictions.
So it's like if I increase the square footage by 100 feet, how much will that impact the predicted price? And then fine tuning the model to reflect that relationship.
Exactly. Calculus gives us the tools to measure those changes and optimize our model for maximum accuracy. It's the engine behind a lot of machine learning training processes.
Wow, okay. You've officially demystified calculus for me, at least a little bit. It's not just about those intimidating equations. It's about understanding how things change and finding the best possible solutions.
Precisely. And when we combine calculus with linear algebra and probability, we get a powerful toolkit for building and understanding machine learning models.
Okay, I'm trying to picture all of this coming together. We've got linear algebra organizing our data, probability helping us make predictions, and calculus fine-tuning everything for accuracy. It's like the ultimate machine learning power trio, but I'm still a little fuzzy on how they actually work together in practice.
Think of it like baking that cake we talked about earlier.
Okay.
Linear algebra gives us the measuring cups and bowls,
Right.
the tools to represent our ingredients, which is our data. Probability is the recipe. It tells us what to combine and in what proportions,
Okay.
helping us understand the likelihood of different outcomes.
And calculus.
Yeah.
Well, calculus is the oven, carefully controlling the temperature and baking time to ensure our cake rises perfectly representing the optimization process.
I love how you brought it back to the cake, but
Yeah.
instead of a delicious dessert, we end up with a smart machine learning model.
Precisely. And to see this in action, let's revisit the example of regression analysis that El Rafey talks about in his article.
Okay, regression analysis. It's all about understanding relationships between variables, right? Exactly. Let's say we're trying to predict how much money someone might spend on a vacation based on factors like their income, age, and how many vacation days they have.
Sounds like a useful model to have. So where does linear algebra come in?
Remember those vectors and matrices?
Yes.
Well, we can use them to represent all of that data. Each person becomes a data point, a vector with their income, age, and vacation days as coordinates. And we can group all of those vectors into a big matrix.
Okay, so we've got our data neatly organized. What does probability bring to the party?
Probability helps us make sense of those data points and look for patterns. For example, we might find that people with higher incomes tend to spend more on vacations.
Right.
That's a probabilistic relationship.
Makes sense. So we're spotting trends and then using that to predict how much a new person who wasn't in our original data set might spend based on their income, age, and vacation days.
Getting it. And this is where calculus swoops in with its optimization superpowers. It helps us find the perfect mathematical formula, our model, that best fits all those data points and makes the most accurate predictions.
So if I'm picturing a scatter plot of all those data points,
Yeah.
calculus is helping us draw the line that best cuts through the data, showing us the trend.
That's a great way to visualize it.
Yeah.
That line represents our regression model, and calculus helps us find its exact slope and position so we can make the most accurate predictions.
Wow, okay. I have to admit, thinking about it like that, all those mathematical concepts suddenly feel way less intimidating and way more like, well, superpowers.
They really are. And once you grasp these fundamentals, you unlock a whole new level of understanding and control over machine learning. You're not just relying on black box algorithms anymore. You're understanding the driving forces behind them.
It's like graduating from machine learning driver's ed to becoming a full-fledged mechanic who can tinker under the hood and who doesn't want to be a machine learning mechanic. That's way cooler than just being a driver.
I couldn't agree more.
So as we wrap up this deep dive, what's the one key takeaway you want to leave our listeners with?
Don't shy away from the math. It might seem daunting at first, but remember, you don't need to be a math whiz to understand the core concepts. And that deeper understanding is what will empower you to truly excel in machine learning.
It's about becoming a more informed, more capable machine learning practitioner.
Absolutely. So the next time you approach a machine learning problem, think about how you can leverage your understanding of linear algebra, probability, and calculus.
Ask yourself, how can I use these tools to represent my data, understand the likelihood of different outcomes, and optimize my model for maximum impact?
Those are the questions that will set you apart.
Excellent advice. And on that note, we'll leave you all with one final thought to ponder. As you continue exploring the world of machine learning, think about this. How might understanding the limitations of these mathematical tools be just as important as understanding their capabilities? Food for thought. Until next time, keep that curiosity burning and happy learning.